So welcome to this lecture of Schrödinger Equation. My name is Wen Han. First of all, I want to thank Slade for lending me this slide. So today's lectures will be mainly comprised of three parts. In the first part, we will look into some history context, like argument about whether light is a wave or a particles, and then how it actually drives and gives birth to quantum mechanics. And then in the next part, we will look into review back what you have learned in the past 2 days and make you realize that there is actually one missing piece. And the whole point of these lectures is trying to fill the gap. So let's go to the first part, the historical context. So quantum mechanics started, the development of quantum mechanics happened from 18th centuries to 20th centuries. And it involved the works from Newton, Huygens, Maxwell, Einstein, and de Broglie. I will give you a little more details afterwards, but these are the summary of it. So all the questions actually boils down to a fundamental question. Is light a particles or a wave? So in 18th centuries, Isaac Newton thought that light is made up of a particles, which is called a corpuscle. And he can explain the phenomenon like reflections as simple as a particle bouncing off a smooth surface. And for refractions is nothing but particles slowing down when it enters a denser medium. And then Robert Hooke's Christian and Fresnel came along and said, oh, light is actually a wave whose speed depends on the medium. And they said that they could equally explain reflection and refractions equally well. And one last defining moment is that this double slit experiment by Thomas Young. And then from this experiment, they actually shows that when you pass the light through the double slit, you receive interference pattern. And then this interference pattern is actually behavior of a wave. And Maxwell comes along and then tells us that light is actually just an electromagnetic wave with well-defined wavelength and propagating in certain directions. So far, so good. This particle is light, a particle or a wave. So for classical physicists, it's a definite yes. But then as time goes along, they found that there is something weird happening, which is the black body radiations and the photoelectric trap. So for black body radiations, as you might have already known, that the classical theory doesn't agree well with the experimental observation, which the energy density of these radiations kind of exploded in a UV regime, which we know is not true. So in order to trying to fit this theory into the actual experimental data, Max Planck came along and proposed that maybe we should treat light, the radiations, as the energy packets with well-defined frequencies omega. And then Einstein came along and extended these ideas by claiming that light is actually just a photons. And this tiny energy packet is a photon. So when this photon is imparted on the metal surface, electron will be emitted. So this kind of agree with the experimental observations that the rate of electron is emitting is not depend on the intensity of light, but the frequency of light that is defined by photon. And this gave birth to quantum mechanics. And at this moment, people aren't sure that light is just a wave anymore, because it can also be a particle. As time goes on, people also starting to ask more questions whether matter is a wave. So matter cannot only be a particle, but it can also be a wave. So this has been proven by experiment of electron interference, where they actually send the electron through a double slit, like the double slit experiment. And then it turns out that they also observed the interference pattern. And this showed the characteristic of wave. And Louis de Broglie came along and then tried to quantify this matter wave with the wavelength of lambda given by h over momentum. So, moving to the next part. Now, what you have learned so far in the past 2 days is that how to describe a quantum system. So, do you guys still remember how to describe a quantum system? So it's through vectors defined by complex amplitude. And then you also learned that what happened when we measure them. So it's defined by Bond's rule. And you can, after the system, the measurement, it collapsed to a certain state. And then you also learn that there are some operations that we can perform, like unitary operations. Now, this 3 point is enough to describe everything you need for a physical system. So to answer that, let's look at how we describe a normal physical system. Then forget everything about quantum, and let's look at the classical physical system. Take a durian, for example. Like you can define how are things for the object, and how far is the durian from the ground, and how fast is it moving upwards. And then you can also measure them. So for example, you can just take a ruler and measure it, and you get some number. And then this durian will also subject to some external force that's interacting with outside. For example, it's like subject to the force of gravity. Right? Now let me pause here for a moment and ask you one simple question. So this scenario is equivalent of like I'm taking a durian above your head, throwing it upwards. So now I have a question for you guys. What would you do in that scenario? A, you will still remain at the same positions. B, you will still remain at the same positions. And C, you will run away. So apparently, as you guys can expect, the durian will fall down eventually, right? So yeah, it's very sensible that you need to go away from the remaining at the position you're at. And why I'm trying to ask this question is that the fact you can predict that durian will eventually fall down, it's because the dynamics is important to describe a physical system. So this kind of brings us to the last point, which is how do things change? So with this 4 points, we can give a full description of a physical system. Now let's look into detail of this point. Now, how are things for the object? We know in classical mechanics, an object can be defined by its positions and momentum. So when an object is moving through space and time, it can be defined as a trajectory in a phase space, x and t, position and momentum. And what can we measure for classical objects? So like I said before, we can just take a ruler or your apparatus, then just get some numbers, some data from the classical object. And the number you get is often a physical quantity, so they are real. And this is very, very different than what you can observe from a quantum system. For example, the superposition of the live state and the dead state. So we know that in quantum mechanics, when you measure a quantum state, it can either collapse to a live state or a dead state, for example. And yep, you will get multiple outcomes after you do the measurement. So for quantum system, you actually need to repeat the measurement many times so that you can get a statistic. So it kind of makes sense to talk about like how probable is a cat dead or how probable is the cat alive. And this is actually just expectation value, or it gives you actually the average of telling you how probable is the state is with a certain error. And this expectation value can be written as in this form. And you might already know this probability. And the written down like in the form of a Bond's rule, right? And you group the term in which is dependent on K together, and this gives you a matrix. This matrix is what we can observe from a quantum system. Now, what are the properties of this matrix? First, it encodes every higher order statistic, which means like if you multiply this Q matrix many times, it's equivalent of taking the power of this diagonal entry power of M. And then the next property is the crucial one, is the diagonal entries of this matrix must be real, because it is what we can observe and measure from the experimental setup. So it must be something that we can read out from the setup. And if you recall from past lectures, if all the diagonal entries are real, then this Q is Hermitian. Hermitian means that when you take the complex conjugate, it doesn't change the matrix. Now let's look at what's going outside. And we can look at an example where a particle is in potential, and then this potential will exert external force on that particles. In quantum mechanics, we will just replace the variable x to an operators, and because these operators must be Hermitian. Now let's look at the last final little part, which is how do things change. Now let's take a look at the Durian examples that I gave you before. When I throw Durians vertically upwards, it can be described like it is losing momentum and then gaining height. It is stopped and then falls down back to the ground. And then, as you know from high school physics, it can be described by Newton's law, Newton's equations. When you solve the Newton equations, it will give you the values of the x and p at different times. And you can, with this, you can define that and predict how the classical object evolved through times. Now, what about the motions for quantum object? As you might already know that the quantum object is described through a quantum state. And this quantum state must be normalized. So whenever you do a time evolutions of a quantum state evolving to the other quantum state, it should be also be normalized. Now, what's missing is how the transformations from the psi p naught to psi p occurs. Right. Now, let's recap what we have talked about. We know how to define the state of the quantum objects, groups or vectors with a complex amplitude. And then we also define what are the physical observables that we can measure from a quantum system. And it has to be permission operators. And then we also look at how we define the external potentials by just replacing the x variable with operators. And the last part is the thing we aren't so sure for now. And this is the missing piece of like trying to give a full description of the quantum system. Now let's guess like how do we construct these quantum time evolutions? We know that quantum time evolutions is nothing but bringing you from a initial state to the other state. And these follow a very similar spirit like Newton's equation analog. Okay, so Newton's equation kind of tells you how the object evolves through the space-time. Now for quantum, if we want to answer how like time evolution is for quantum systems, we need to answer like what type of the transformation can make this happen. And what are the mathematical forms does the time evolution take? And what is the physical interpretations? So we know the first 2 points must be what we have already known, what you have already learned in the last 2 days. Because we're physicists, we need to give some physical interpretations to this abstract idea we have. So it is just an extrapolations from the abstract ideas. Now let's look at how we define the transformations. We know that the transformations must bring a valid quantum state to another valid quantum state. A valid quantum state, I mean something like the state must be normalized. So this has to be true no matter the value of t. Okay. Another word of saying this is that the transformation itself must preserve the inner product. So as you guys have already learned in the previous lectures, what are the operations that preserve the inner product? It's a unitary transformations, okay? So the unitary transformation of a quantum state is nothing but you're applying a unitary matrix on the initial state in vectors and result in another vectors. And this unitary matrix cannot guarantee that the inner product doesn't change. Okay. Now let's look at the most simplest form of this unitary matrix. So let's say now we have the transformations that bring the state psi t to psi t. So we see the psi t, they are the same instance. So this corresponds to the transformation that does nothing. So do you guys know that what are the matrix that when applied onto a vectors, it will go in the same vector itself? Exactly. So it's the identity matrix. So we know that identity matrix is actually also a unitary matrix. Then now let's get a bit more ambitious. Like we're trying to know like what are the U that can take you not only from the current state to the same state, from current state to the state somewhere in the near futures. So this is equivalent of writing down the U in this form. So this can be written as the transformations that taking U from the state in T to the state in T plus delta T. So delta T is something very small, it's like milliseconds or something even smaller. So one useful tool that we can apply here is linear extensions, which basically say that if we expand, if this delta x is small enough, and then we expand around x equals 0, you can written down this in a linear form in x. So in a very similar fashion, we will apply this to delta t, and in turn, we can write down the unitary matrix in form of the sum of identities plus something. So what this is actually about, a sanity check, let's find this U onto the state we have, and then result in this form. And we can quickly check that if this delta t is 0, we get back to just psi t. So this is equivalent to just identity matrix that you have learned just now. Now, what are the physical interpretations? So you can see these are just bunch of vectors. So another way of saying this is that the state you evolve in the near futures is nothing but the sum of these two vectors. Okay. And this defines a forward time evolution because you're actually bringing a state from t to t plus delta t. Now, what about the inverse transformations? We know that if you take inverse on a unitary matrix, it results in a complex conjugate. So when you take the complex conjugate on the expression we had just now, you get this form. So what this form is actually telling you is that this inverse transformations is a transformations that brings you from the state e plus delta t back into t psi t. Now we know that the state of psi t and psi t plus delta t are the same on both sides. So this kind of places the specific restrictions on the matrix WT. And now we're going to find out what the WT actually is. So this can be done by just comparing the two vectors because they are opposite in directions. And we know that when you sum the opposite vectors together, you get 0. And this kind of tells you that, well, when you take a complex conjugate on the matrix W, it will give you some additional minus sign. Now, how do we look at this in terms of Hermitian matrix? We know that Hermitian matrix, when you take the complex conjugate, Hermitian matrix is unchanged. So in order to have one extra minus sign, we need to introduce an extra complex number, I below. We'll have what the form W is. Now let's put this back into our linear approximations. And then just move the psi t to the left-hand side. As you might have already noticed, this looks like the approximation form for the differential equation. So as delta t goes to 0, the linear approximations becomes exact. And then we get the differential equations. And this is what we're looking for. This is the Schrödinger equation, and it defines the time evolution of a system. And with this, we have found the shapes of our missing piece. Now this is just a tool. Now let's quickly refresh what I have talked about. First, the time evolutions is a unitary transformations that preserve the inner product. And then it satisfies the Schrödinger equation. And you can write this Schrödinger equation in the other form by rewriting the psi t as the unitary transformation of the initial state. And when you remove the initial state, you get some alternate form that describes the dynamics of the unitary transformation. Now, one last question is that what is the physical interpretations of the Schrödinger equation? Well, we know that H must be Hermitian, but what is the correct choice of this H? We know that different H will give different dynamics that involve the system differently. And we're also trying to ask that what H physically represents. Well, let's consider light as an example. If we have only one photon with fixed polarizations and fixed charge, you have only one degree of freedom. So this basis that's described, this matrix, is nothing but single dimension vectors. Now let's consider when we allow different values of energy, we actually introduce more degree of freedom. Now the question is, how do we actually, what are the properties of this degree of freedoms? So these are the rules that okay, which give the complete descriptions of the system. So the first property is orthogonality. So this is basically means that it is orthogonal and it is normalized. So what this means is that the energy of the photon can only take one of the possible values. So for using the example from the previous slide, let's say the photon can only take, it's assigned with different frequencies, like two frequencies. One frequency corresponds to red colors, and then the other frequencies correspond to blue colors. So what happened in an experiment, when you're trying to measure only the blue photon, you will get some binary outcomes. Whether it is a yes, it is a blue photon, or no, it is not a blue photon. So these binary outcomes can be represented in this form. And you will be, so these are basically saying that if you have like a red photon and then the experiment, it gives you red photon, then you get something non-zero. But the normalization condition requires it to be once. So in a similar fashion, if you want to observe a red photon, but it gives you a blue photon, so you observe nothing. So that's the zero stands for. Okay. And the other properties is completeness. So like I said before, the sum up of these different, whether the photon is in blue colors or the photon is in red colors, the sum of their probabilities must be equals to 1, which means that the energy of the photon must fit on one of the possible values. So you can't find like, this kind of experimental setting, you can't find a third case, like the photon is not blue and not red. So in this form, you can rewrite this using Born rules, and this group can add together. So what this completeness relation is actually telling you is that the sum of all of the bases is an identity. Okay. Now, how does the photon evolve in time? Let's consider a system with no energy in or out. So the probability you measure your initial state is same with the future state is equal to 1. And the way you can write down for this state, we can add this form, and then we know that photon is a periodic functions with frequencies. So we can also rewrite the ET of this form, as you can quickly check when we put it in, we will get 1. Okay. And this EN simply states means that you have only one entry is non-zero, and then the other entry is 0. Okay. And then that is what we mean by orthogonal. Now let's go back to Schrödinger equation. Let's plug in what we have on the previous slide. We know this is the result from Png and Einstein. Telling us that this energy packets like this photon is described by h bar omega n. And we rewrite this a little bit. And when we get a space form, next we will apply En and T from the right hand side. So in this part, the U and U dagger will become identity, and we just go and write it down. And we will arrange a little bit to group the element together. From the completeness relation, we know this is identity, right? So we can just omit it. We just write it out. And when U is U unitary matrix applied on initial state, we will get some evolved state here. And then this are the final form. Now let's look at how this actually tells us anything useful about HT. So by direct comparison, we can write down like, okay, this HT has this form. And then what it actually tells us is that the ENT in front is an energy measurement outcome. And then the state, the basis at the behind is the post measurement state. And post is a summation, so this HT is a physical observable energy, where the ENT corresponds to the real value. From here, we have recovered that how does the photon evolve through time. It's described through this HT, which is a Hamiltonian written down in this form. And because this expression is general enough, so it can also use to describe any other quantum state. So let's quickly recap what we have learned. You know that time evolutions is a unitary transformations, and then it satisfies the Schrödinger equation. And then in the Schrödinger equations, the HT is the Hamiltonians that defines the energy of the system. And with that, we have completed all the puzzles. And then you have everything you need to describe a quantum system. First part being you need to know how to describe quantum state. Then you also know that the physical observable is information operators. And then you also know how to describe these external potentials by replacing the variables in operators. And then at last, in order to describe how the quantum system evolved, we can use Schrödinger equation. So the take-home message of today's lectures is that historically there is much about modern understanding of matter. It came from our attempts to uncover the nature of light, whether it is a wave or particles. And then we know that light and matter have both wave and particle characteristics. And then in later section, we learned that dynamics of a quantum system was described by the Schrödinger equations. And then the Hamiltonian energy of the system governs its time evolution. This will cover almost all of the building blocks that stands at the foundations of quantum mechanics. So in quantum mechanics, we write all the things you have learned in more rigorous format. This is what we call as the postulate. So in the first postulate, the state of a closed system is described by state vectors. We have complex amplitude, and then every measurable physical quantity Q is described by Hermitian operators. This matrix Q and the possible values of Q are eigenvalues of Q, like the capital Q. And this, of course, must be real. And then in this next postulate, the probability of the measurement is given by Wronski. After the measurement, the system will collapse into the state given by QK. Now the last piece of the puzzle is that the Schrödinger equations govern the time evolution of the system. So with all these tools, you are ready to play with most of the quantum system. But actually, there is something more, which will be elaborate more in the next lectures, which is what if we have more than one quantum system? So as you have already know from the popular science, that entanglements normally requires more than one quantum system, and this kind of gives many bizarre phenomena. This part will be taken over by the next lecturers. With that, I'm reaching the end of the lectures. I hope you guys did learn like what is the time evolutions governed by the Schrödinger equations. Thank you very much.